This meeting is being recorded.
Hello, everyone. I hope you studied chapter 1 and you know everything about chapter 1. This is chapter 2, which talks about the molecules that are inside of a cell. So I give you the definition of an atom. Now it's a definition, it's a molecules that we are going to talk about. Pretty much we human, all living organisms are made up of 4 macromolecules, if you would, and I go over them. This is a long chapter. I will not be able to finish all of it in one session, so I have to break it up to 2. So let's see, and as I said, I want each session to be half an hour. So let's go on and go over. Okay, the learning outcomes, make sure you know that distinguish between atoms and elements. You know, atoms are the smallest parts of an element. And then atoms are made up of electrons, protons, neutrons, all of that. And then, so we'll talk about this a little bit today. So matter, this is the definition of matter. Anything that has mass and takes up space, it's a matter. So your body is a matter. And elements are basic building blocks of matter, cannot be broken down by chemical means. Over 90% of our body is made up of only 4 elements, which is carbon, nitrogen, oxygen, and hydrogen. These are the different 4, I said there are 4 building blocks. That's not the same 4 that I was talking about at the beginning. At the beginning, I was talking about 4 building blocks. These are the, you and I, most all living organisms are, they're pretty much made up of these 4 elements: carbon, nitrogen, oxygen, hydrogen. You will see. I think as this chapter goes on, you will see it better. Here is a periodic table, if you would. And in this periodic table, you do have these elements: hydrogen, helium gas you're familiar with. They put it in balloon, it goes up. And then some of the things that very common in living organisms is here is a carbon, nitrogen, oxygen, and hydrogen. So these 4, we are made up of these 4, and primarily carbon right here. So carbon is the main element that we are made up of. The backbone of our life is carbon. And then, of course, this is not all of the 109, 110. Now, I don't know, the numbers are increasing. This is not all of 109 elements on periodic table. The salt that you eat, we will talk about it, is made up of sodium right here and chloride. Okay, so we will talk about some of these that, of course, you should be familiar with. Atoms, the smallest unit of element that remains, its physical and chemical properties. We talked about that. Atoms bound together to form molecules. Parts of an atom are called subatomic particles, which is neutron, proton, and electron. Neutron, as it names it appears, it does not have any charge. Proton is positively charged, and these 2, proton and neutrons, are in the nucleus of an atom. Later on, you're going to be familiar with that term. I'm going to toss this term at you later on. A nucleus of a cell is different than nucleus of an atom. 2 different things, completely different. Okay, so do not get the terminology mixed up. So these 2 make up the nucleus of an atom, okay? And then the electrons, they orbit, they are negatively charged, and they orbit, they go as a circle around the nucleus. If this is the nucleus, they go around the nucleus like this. They orbit at a high speed, so it's called electron shells. Here it is, a good picture of it. So you have, here is, for example, carbon. It has 6 proton, 6 neutron, and then of course it has 6 electron. For this course, anytime for the lab stuff and you know, the simulation labs. So anytime you have 6 proton, it means you have 6 electron. You have 7 proton, it means you have 7 electrons, and so on and so forth. Not always the number of neutrons and protons are same, okay? Not always they are same, but for our class, the number of the proton and the number of the electron, these are electron right here, they are same for our class. Oxygen is 8. Do not memorize these numbers. When you take chemistry class, you possibly have to memorize them, but for our class, you don't have to know that carbon has 6 electron or 6 neutron. And okay, atomic number, the number of protons differs in every element. Of course, you saw it in the last slide. For example, carbon has, look at carbon. Carbon has 7. Carbon has 6 proton, and then nitrogen has 7, and oxygen has 8, and hydrogen has 1. Okay, so that's atomic number, number of protons. Mass number, sum of the number of protons and neutrons. That's a mass number. So combination of these two together, proton and neutron, is a mass number which makes up the nucleus. Protons and neutrons each have a mass equal to 1 atomic mass unit AMU. Electrons have a negligible mass. They have a small mass. They're just like a cloud. There's not much there, but you know, you will see they are very important in chemical bonding in a minute. Atomic mass, the average AMU for all isotopes of that atom. Okay. Isotopes, atoms of the same element with the same atomic number, but a different number of neutrons. Okay. Carbon is an example of that, is an isotope. When you go deal with radioactive material, they have different isotopes. Excuse me, let me get some tea or coffee that I can talk to you. My throat gets dry, sorry about that. But anyhow, let's talk about radioactive material. We'll not focus on it too much. I'm not too crazy about it, but let's move on and at least mention this. Your textbook mentioned it. Radioisotopes are unstable isotopes. They emit energy called radiation. So that's what happens when you go for radiotherapy. Radiation can damage cells. Usually they are reproductive cells, and cause cancer. When you go for radiation therapy, that's what I was thinking about when they said that. Of course, radiation, like the sunlight is a radiation. You do need it, but too much of it, it can cause cancer. Useful for image the body, killing bacteria in food. Sterilization equipments, ultraviolet light, they use it to kill bacteria and sterilize equipment. And of course, ultraviolet light, the high wavelength of it is not good for us either. Here it is, they're showing you imaging. They're using these imaging for either radioisotopes or other equipment. Okay, let's move on. Molecules, atoms based to bonds together. There are 4 different bonds, and I'm not sure which one is your textbook. I think he talks about all of them, except maybe one of them he doesn't talk about. But molecules are atoms bonded together, can be made up of same atoms or different atoms. This is, that would be like oxygen or water. So 2 oxygen molecules, when they come together, so they form oxygen gas. And then water molecules, you have 2 hydrogen, and with 1 oxygen right here, they bond together, and that is water. Compounds, molecules made up of different atoms, that is H2O, not O2, and then 2 types of bond, joint atoms, ionic bond and covalent bond. Yeah, okay, we'll talk about both of them. Atoms are most stable when their outer electron shells are valence shell is full. And I'll talk about that. I guess pictures will say 1,000 words. During an ionic reaction, atom donate or take one electron to fill their valence shell. This results in the formation of positive or negative ions, and we'll talk about that ionic bond, the attraction between a positive and negative ion. Okay, the salt that you put in your food right here, the salt that you put in your food, your French fries or whatever, it is made up of sodium, I already mentioned that, and chlorine. So what happens right now, 8 is a magic number, you guys. Remember number 8. So I might ask questions during the exam. 8 is the magic number. The sodium in the nucleus, of course, you have 11. There should be 11 right here. Do not memorize those numbers. 11 proton, so he has 11 electrons. Here is 1, 2 in the first shell. In the second shell, he has 8. Right here, 1, 2, 3, 4, 5, 6, 7, 8. And then the very outer shell, it has 1. So it makes up 11. Okay, chlorine, it has 17. Right? In the nucleus, there are 17 protons. So in the first shell, how many? 2. In the second shell, how many? 8. Remember, 8. In the third shell, it has 7. 2 plus 8 is what? 2 plus 8 is 10, right? 17 minus 10 is 7. So 1, 2, 3, 4, 5, 6, 7. It has 7 electrons in the outer shell. This guy has 1 electron in the outer shell. They're unhappy. Both of them are unhappy. So what happens? This one, sodium, it transfers, it give away, if you would, its electron to chlorine. Chlorine now in the outer layer has 8 electrons, okay? And now, since this gave up its electron to the chlorine, now sodium has 8 electrons. They both are happy. They both form a bond, which is called ionic bond, right here. It's called ionic bond because it transferred the electron to another one element, transfer electron to another element. And then right here, 8 on the outer shell, 8 on the outer shell. Since this guy transfer electron, this is a positively charged, we call him cation. You probably have heard of that word. And then this guy is negatively charged, is anion. Right there, okay? So chlorine is an anion, negatively charged, and a lot of times you will see chlorine written down, oh, sorry, my bad. Chlorine is written down like that, and sodium is written down like that, so you know what they are, okay? So that's ionic bonding, when you transfer electrons. Covalent bond, on the other hand, is when they share electrons. Okay, so when you have atoms share electrons to fill their valence shell, oh, that's the valence, the term valence. This is the outer shell, it's a valence, okay? Remember that term, I tossed that to you before, it's a valence. So atoms share electrons to fill their valence shell. Each atom contributes 1 electron to share pairs. The electrons spend time in the valence shell of both atoms. It's unlike here, you know, this is not sharing electrons. They are transferring electrons. And then the electron spends time in the valence shell of both atoms. Double covalent bonds share 2 pairs of electrons, and you see that triple covalent bond share 3 pairs. So those are the maximum you can have with double covalent bond or triple covalent bond, depicted by 1 or 2 straight lines. Okay, let's look at it. Now I'm talking about covalent bond. I hope you're with me. Here's a hydrogen right here. Here's a hydrogen, 2 of them, right? And then they go share this one electron, share that one electron with oxygen. Okay, so when they're sharing electron, the diagram would be something like this. Okay, that would be the diagram look like H2O. This is a hydrogen, hydrogen, and of course this is oxygen. So they are sharing electrons, and the way they write them, you will see it for the rest of semester. They write it like this: O, H, H. So that line is indicating a covalent bond. One covalent bond between that hydrogen and this oxygen, one covalent bond between that hydrogen and this oxygen. Okay, so I hope you understand what I'm saying. And you put two oxygen together right here. So oxygen has 6 electrons. Oxygen has 6 electrons. So it has to, in order to reach the maximum number of 8, remember this, the 8 is a magic number. Of course, hydrogen is happy with 2 because hydrogen only has 1. Hydrogen cannot have 8. The rest of elements in periodic table will have 8 in their outer shell. So the very inner shell is 2 electrons. The very outer shell is 6 electrons. So it has space for 2 more electrons, right? So here is 2 oxygens. And what happens now, if you look at it, this oxygen right here, it has 8 electrons orbiting outside of it. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 8 electrons orbiting outside of it. 1, 2, 3, 4, 5, 6, 7, 8. How many they are sharing together all together? 4. How do you write these 2 molecules? Here's an oxygen. Here is an oxygen. And the way you write it down, like that. Okay, 2 covalent bond. And the way you saw it before, it is O2 right here. Okay, so you saw examples of covalent bond. Covalent bond are much more common than ionic bond in living organisms. You will see them. These are your progress. Please check and make sure you understand what's going on. And then describe the properties of water. That's what is coming up. I spent only 15 minutes so far, you guys. Yes, I've been 15 minutes. Let's spend a few minutes on water. And then we'll go ahead and mention the materials for the second part of the chapter 2. Water is most abundant molecules in organisms. Of course, bacteria is full of water. You and I make up about 70% of the total body weight. Water is polar molecule. And what does that polar means? Okay, I give you that definition. Oh, he gave you the definition. Electron spends most time around the oxygen than hydrogen, creating a partial negative charge. Okay, the definition of polar, he's not giving a good definition, I don't think. A polar molecule, it means one end of the molecule is negatively charged and one end is positively charged. One molecule, like water. If you look at water, you might see, yes, correct, he mentioned it. If you look at the water molecule, what happens, here's my pen. What happened, the hydrogen molecules, hydrogen elements, I should say, hydrogen elements are right here, are positively charged. And look at the oxygen, on this end is negatively charged. Oxygen attracts the shared electrons and is partially negative. Hydrogen are partially positive. So here is positive, oxygen, hydrogen positive, and of course, oxygen is negative. So that molecule is a polar molecule. One molecule. That one molecule, one end of it, if you look at it, one end of it is negatively charged. The other end are positively charged. And you will see that a lot in biological settings. The other, he talked about polarity, and then let's talk about hydrogen bonds. I guess you have to understand, oops, sorry. You have to understand polarity right here in order to be able to understand hydrogen bonds. So you remember we already talked about two bonds, covalent bond, ionic bond, and then the other bond right here is hydrogen bond. Hydrogen bond, the definition of it, make sure you know the definition of each one of these bonds. Attraction between a slightly positive hydrogen to a slightly negative oxygen or nitrogen. So depicted by dotted lines, relatively weak bonds. Okay, covalent bond is the strongest bond among these three that we talked about. It takes a lot of energy to break covalent bond. It doesn't take much energy to break hydrogen bond. It doesn't take much energy to break down ionic bond in salt that we talked about. Here it is. Great, let's talk about it. This is a good diagram. Here's a water molecule, of course, hydrogen, right? Oxygen, you already know about this. So what happens, as we said, oxygen is negatively charged and hydrogen is positively charged. And if you look, this hydrogen is attracted to this oxygen. This hydrogen is attracted to this oxygen. So there's an attraction. There's no physical bond. There is no transfer. There is no sharing electrons. It's nothing like that. Since this is a polar molecule, one end is positive right here, and the other molecule, in this case, same, water, they are attracted toward each other. Okay, so this bond, the dotted line here, is hydrogen bond. So hydrogen bond. Okay, not James Bond, hydrogen bond. Same thing. The rest of the diagram is same thing. He's showing you a hydrogen bond between oxygen and the hydrogen here. Oxygen and hydrogen here. Oxygen and hydrogen here. They are attracted towards each other. They are not physically bounded to each other. So that is called a hydrogen bond. You will see it. We have hydrogen bond in DNA. We have hydrogen bond in protein molecules. We have hydrogen bonds all over the biological settings. Okay, properties of water. Again, I'm not gonna talk about it too much, you guys. Water is liquid temperature, room, yes. One thing I would like to mention, amount of heat required to raise calorie. I like to talk about calorie a little bit, very important. To raise 1 gram of water, 1 degree Celsius. If I have in a beaker, in a container, I have some water, in this case, 1 gram, it's a very small amount, okay? And I have some heat right here, I'm heating it up, okay? I'm heating it up, and I have a thermometer here, right here, you know, these are the temperature of thermometer. When the amount of energy I spent right here to increase the temperature of this water, 1 gram of water, 1 Celsius, you spend 1 calorie. Okay, that's what the definition of calorie is. When you spend 1 gram, which is a very small amount, that's why 1 calorie is very, very small, 1 Celsius. 1 calorie is very, very small number. So that's why when you read food labels or other things, they say 10 calories, it means 10,000 calories. So what they did, they instead of 1 gram, they said 1,000 gram. Okay, let's raise the temperature 1 Celsius. I think it's from 24 to 25. It makes a difference. What temperature you raise it, and that the amount of calorie you spend is 1,000 calorie. Because 1 gram is so small, they went to 1,000 gram, which is almost 1 liter. Okay, so prevent large temperature in body, high vaporization. You know all of these. The main thing I'm concerned about is the definition of the calorie, that you'll be familiar with it. Here they talked about the diagram of the calorie, temperature, and water. And the calories are expended. Properties of water continued. Water is a universal solvent, if you would. That's the one I use a lot. Universal solvent, it means a lot of things can be dissolved in water. Not everything, but a lot of things can be dissolved in water. And right now you can see salt. When you put salt in the, right here, I'm talking about this diagram, you guys. When you put salt in water, they dissolve. Sodium separates from chlorine, okay? That's what happens. And they are surrounded, the chlorine is surrounded by water. So a solution, the definition of a solution is solute, whatever solute is. It could be sugar, it could be salt, it could be anything that can be dissolved in water. If it is not like sand, it's not dissolvable in water, that's not a solution. They call that a suspension, okay? So a solution, whatever, like oil and water, that is called a suspension. It's not a solution. So a solution is whatever is dissolved in water, in this case, salt, sugar. Salt dissociates or separates when it's dissolved in water, facilitating chemical reactions. Okay, properties of water continued again. Water is a solvent continued. Polar molecules attract water, so hydrophilic, as you know, and your prefix suffix is hydro, it means water. And philic, it means love, like, if you would. So polar molecules attract water, and the molecules that one end is positive, one end is negative, of course they love water, because one end of water is positive, one end of water is negative, and the negative end of the water goes toward the positive end of the other molecule, and the positive end of water molecule goes to the negative, I already said that. Negative end of water molecule goes to the positive end. Anyhow. Hydrophobic, hydro means water, as you know. Phobic, it means scared, dislike. Right here, molecules that do not attract water are nonpolar. In nonpolar covalent bonds, the electrons are shared equally, no partial charge. This is, that is vegetable oil is nonpolar, so one is often water. Cohesion, adhesion, yeah, just know the definitions. I do not have much to say about those things. As liquid for food becomes less dense and freezes, as you know, when water molecule freezes, ice floats on top. It does not go on the bottom. Unlike a lot of other molecules, when they are frozen, they usually go, they become more dense, they go on the bottom of the water. Okay, acid and base. That's something I do want to spend some time on it. I don't know how long. It's been another 5 minutes. I think we can finish acid and base. So that would be half an hour that I talked to you guys. Acids are substances that dissociate in water, releasing hydrogen ions. Okay, that is hydrochloric acid, like HCl, is in your stomach. Is produced by stomach acid and digestion. So hydrochloric acid can break down to hydrogen and chloride. Bases are substances that take up hydrogen ions or release hydroxide ions. And in that case, sodium hydroxide, which is a strong base and releases, like baking soda, as sodium hydroxide. So that's a base. I should quickly write it down here. The acid, there is a scale of 0 to 7, if you would. Here is 0, I'm sorry, 0 to 14. 0 to 7 is acid, and 7 to 14 is a base. So if you have a base, the pH has to be, we'll talk about pH, small p, capital H. Percent hydrogen, it stands for percent hydrogen. So if you have a base, the pH is between 7 to 14. pH scale is measured acidity. Okay, alkalinity is range 0.7, 7 is neutral. It's very, very hard to get perfect pH 7. Even your pH in your blood, pH of your body, except your stomach, all over your body, the physiological, they call it physiological pH is 7.4. Okay, 7.4. So that's a physiological pH, they call it physiological pH. Okay, and then a pH below 7 is acidic. We talked about all of that. Here's a nice diagram giving you a few examples. Hydrochloric acid, I don't think it's 0. It's very, yeah, right here. Okay, stomach acid. Okay, I thought he's talking about hydrochloric acid. Yeah, very strong hydrochloric acid. It can reach 0, but absolute 0, I don't think it's possible. Sodium hydroxide, household ammonia, bleach, household ammonia, and then Great Salt Lake. So these are some of the examples. Please be familiar with them. Urine is acidic. Coffee you drink every morning, the tea I drink, the coffee I drink, they are all acidic. Of course, the water that we drink, it's near 7. It's not perfect 7. It depends where we live, which part of the country we live, but it's usually on acidic side, 6.8, 6.6, 6. I'm not sure. You can look up, see what is the pH of the water in your area. But obtaining perfect pH of 7, it is very difficult. They have machines that cost $1 million or so, and you get a little bit of it for pH perfect 7. So when you go to a grocery store and you buy those deionized water, that is not perfect 7. So anyhow, buffer is a solution that resists changes in pH when acids or base are added to it. That's called a buffer. You've heard of that term in English language, buffer zone, buffer this, buffer that. So important within the body and ecosystem as a whole, pH values needs to stay within a narrow range. This is a carbonic acid bicarbonate ions, and he's giving you examples of course, when we get to the respiratory system, we'll talk about this a little bit more. Okay. Here's a checklist, and here's a learning outcome. Okay, that's what I want to talk about next. I think I'm going to stop this, and then we start the other one. And the 4 organic molecules, I call them macromolecules. That's what we are going to talk about. The 4 major organic molecules, he's not talking about carbon, hydrogen, oxygen, nitrogen. No, we are not talking about that. We're talking about organic molecules, which are carbohydrates, lipids, proteins, and nucleic acid. And then I need to spend a little bit of time. Let me see how much I talked today. Yeah, I talked for half an hour. So anyhow, all right. I think I'm going to stop here, and then we pick up the second portion of this chapter from here. All right, guys.